Today we're going to take a detailed look into the transformations of the graphs of functions. We all know that a flat mirror enables us to see accurate images of ourselves and whatever is behind us. When we tilt the mirror, the images we may see shift horizontally or vertically. But what happens when we bend a flexible mirror? Like a carnival funhouse mirror, it presents us with a distorted image of ourselves, stretched or compressed horizontally or vertically. In a similar way, we can distort or transform mathematical functions to better adapt them to describing objects or processes in the real world. In this section, we're going to take a look at a few of those different kinds of transformations. And to get started with, as an intro to transformations of graphs of functions, I would encourage you to pause this video and take 5 to 10 minutes, visit desmos.com, and type in the function f of x equals x squared, and simply manipulate that function by substituting in values for a, b, c, and d. All right, hopefully you spent some quality time visiting desmos.com and manipulating that quadratic function f of x equals x squared to kind of get a feel for the different types of transformations that could take place when graphing those functions. One simple kind of transformation involves shifting the entire graph of a function up, down, right, or left. The simplest shift is a vertical shift, moving the graph up or down, because this transformation involves adding a positive or negative constant to the function. In other words, we add the same constant to the output value of the function, regardless of the input. For a function such as y equals f of x plus d, where d is greater than 0, that's going to shift our graph up d units. If y equals f of x minus d is given, where d is again positive or greater than 0, that's going to shift our graph down d units. So we just saw that a vertical shift is a change to the output or outside of the function. We'll now look at how changes to the input on the inside of the function changes its graph and meaning. A shift to the input results in a movement of the graph of the function, left or right, in what is known as a horizontal shift. For a function such as y equals f of x plus c, the function f of x shifts the graph to the left, c units. Now you might be thinking, why does adding c move the function to the left in the negative direction? Well, imagine you're going to inherit a fortune when you're at the age of 25. If you change that to be age plus 4 equals 25, then you'll get it when you are 21. Therefore, adding 4 made it happen earlier. So a quick way to remember which way to move the graph, left or right, just simply set whatever inside the parentheses, in this case x plus c, and set it equal to 0. Your solution will tell you which direction to move and by how much. Now for a function y equals f of x minus c, where again c is greater than 0, that's going to do the opposite and shift our graph to the right, c units. Now another transformation that can be applied to a function is a reflection over the x or y axis. A function such as y equals negative f of x has a vertical reflection, and a vertical reflection reflects the graph vertically across the x-axis. While the function y equals f of negative x has a horizontal reflection. A horizontal reflection reflects the graph horizontally across the y-axis. Notice that the vertical reflection produces a new graph that is a mirrored image of the base or original graph about the x-axis. The horizontal reflection produces a new graph that is a mirror image of the base or original graph about the y-axis. All right, moving forward. Adding a constant to the inputs or outputs of a function changes the position of a graph with respect to the axes, but it does not affect the overall shape of a graph. We're now going to explore the effects of multiplying the inputs or outputs by some quantity. We can transform the inside input values of a function, or we can transform the outside, which is our output values of a function. Each change is going to have a specific effect that can be seen graphically. When we multiply a function by a positive constant a, we get a function whose graph is stretched or compressed vertically in a relation to the graph of the original function. If the constant a is greater than 1, then there's going to be a vertical stretch. If the constant a is between 0 and 1, then there's a vertical compression. Now let's consider the changes to the inside of a function. When we multiply a function's input by a positive constant b, we get a function whose graph is stretched or compressed horizontally in relation to the graph of the original function. If the constant b is greater than 1, then there's a horizontal compression of the function. If the constant b is greater than 0 and less than 1, then there's a horizontal stretch. Now, in addition to looking at the transformations of the graphs of functions, we're also going to revisit inequalities, and we're going to discuss today how to graph a radical and absolute value inequality. Starting with graphing radical inequalities, we're going to graph using the same method as we did graphing any other inequality before. Begin by finding the domain restriction, which is what makes the radicand equal to 0. And the reason why we want to do this is recall that any negative value inside a radical would make that inequality imaginary, and we cannot graph an imaginary root. Next, you're going to want to determine whether the radical inequality has a solid or dotted line, and that's going to be based on the original inequality. If it's equal to, remember, it's going to be solid. If it's just greater than or less than, you're going to use a dotted line. Next, we're going to determine where to shade, and to do that, we're going to test a point. You're either going to test a point below the radical or directly above the radical. And then where you're going to shade is from the end point, which is the original point that you started with, and you're going to shade directly straight up or directly straight down in the respected region. So let's go ahead and look at this first example. It's asking us to graph y is greater than the square root of 2x plus 4. So step 1, we're going to begin by finding our domain restriction by setting our radicand equal to 0. So our radicand is 2x plus 4. If I set that equal to 0, I get 2x equals negative 4, x is equal to negative 2. So in regards to my table, I know I'm going to start at x equals negative 2. And if you recall basic graphs of radicals, a radical starts at an endpoint and continues on forever in one direction. So in this case, we're going to be moving to the right. So I'm going to pick points to the right of negative 2, which would be negative 1, 0, 1, and 2. Now, to figure out our corresponding y values, I'm going to start by plugging negative 2 into the original inequality for x. So 2 times negative 2 is negative 4. Added to 4 is 0. The square root of 0 is 0. Plug in negative 1. 2 times negative 1 is negative 2. Plus 4 is 2. And the square root of 2 is approximately 1.41. Plug in 0. 2 times 0 is 0. Plus 4 is 4. The square root of 4 is 2. Plug in 1. 2 times 1 is 2. Plus 4 is 6. So the square root of 6, which is equivalent to me typing it into my calculator. I get 2.44. And then plug in 2. 2 times 2 is 4, plus 4 is 8. So the square root of 8 is approximately 2.82. Let's go ahead and plot these points. So we got negative 2, 0. Negative 1, 1.41. And I'm just approximating these values. 0, 2. 1, 2.44. And then 2, 2.82. And you can see here that I have a radical that's starting at this endpoint at negative 2, 0, and it's continuing on forever in one direction, in this case to the right. And remember, we said this should be dotted because this inequality is just greater than. Now at this point, we need to test a point. And I need to test a point either inside the radical or directly above the radical. And so I'm going to test 0, 0. And so I'll plug this into my original inequality. So 0 is greater than square root of 2 times 0 plus 4. And I get 0 is greater than square root of 4 is 2. And that is false. So I know 0, 0 is not part of my solution set. So I know I'm going to be shading directly above this radical inequality. And remember, it's going to be directly straight up from this endpoint. at negative 2, 0, and then it's everything above it. And that would be my solution set, which is a region of solutions to this radical inequality. All right, let's go ahead and look at our second example, which is asking us to graph an absolute value inequality. Now, to graph an absolute value inequality, you're going to, again, use the same method as graphing other inequalities. You're going to begin by finding the vertex, determine whether it's solid or dotted, and then you're going to either shade above or below by testing a point. Remember, absolute value graphs have a V shape. So in this example, we have graph y is less than or equal to 1/3 absolute value of x minus 1 minus 4. So step one, start by finding the vertex. Now what's nice about this problem is it's in vertex form. So we know the vertex right off the bat. And we know this from our transformations now. X minus 1 means it's going to be shifted to the right one. And then minus 4 on the outside means we have a vertical shift down 4. So my vertex is 1, negative 4. Let's go ahead and plot that point. Going to the right one, down 1, 2, 3, 4. And since this is a V-shaped graph and that's my vertex, I want to pick a few points on either side of that x value of 1 for my vertex. So I'm going to pick points to the left of 1, which would be 0, negative 1, and to the right of 1 would be 2 and 3. Let's go ahead and plug negative 1 into that original inequality for x. So we have negative 1 minus 1, which is negative 2. The absolute value of negative 2 is 2. Times it by 1/3 is 2/3, minus 4. And we get approximately negative 3.3. Plug in 0. 0 minus 1 is negative 1. Absolute value of negative 1 is 1. Times it by 1/3 is 1/3, minus 4. Gives us approximately negative 3.6. Plug in 2. 2 minus 1 is 1. Absolute value of 1 is still 1. Times it by 1/3 is 1/3, minus 4. And that's equivalent to, again, negative 3.6. And hopefully you can see that on either side of my vertex, the same increments to the left and right are going to be symmetrical, similar to what we saw with quadratics and parabolas. So this last part of my table for when I plug in 3 should be 2/3 minus 4, which is approximately negative 3.3 again. So let's go ahead and plot those points. We got negative 1, negative 3.3. Again, I'm just approximating this. 0, comma, negative 3.6. 1, negative 4 we got. 2, negative 3.6. And 3, negative 3.3. And so you can see here, it's starting to take the shape of a V. And looking at my original inequality, it's equal to, so we know this should be a solid line for each part of my absolute value. And now I need to test a point, and I'm either going to test a point above the absolute value inequality or below it. So maybe I want to test 0, 0. So we got 0 is less than or equal to 1/3 times the absolute value of 0 minus 1 minus 4. Let's clean this up. 0 minus 1 is negative 1. Absolute value of 1 is 1. 1 times 1/3 is 1/3 minus 4. And so we have to figure out, is 0 less than or equal to 1/3 minus 4? And that is false. So we know that 0, 0 is not included in the solution set, so I'm going to be shading below this absolute value inequality.